Alright, let's try to understand something which sounds fancy, looks fancy, spells fancy, but believe me, when we decode that, it is based on some handful principles which you are aware about. So it would be a nice lesson in dispelling the myth that it's tough. The title is Constrained Motion. Fancy word alert. What is constraint? Constraint means restriction. When you apply a restriction on a system or a part of a system to behave in a certain way, it is called constrained motion. I'll leave you with a picture and the idea before I go ahead into the math part of it. Look at this picture. It's a classic scene out of a not that great movie, but a cartoon or animated movie. Two friends are actually in a cliffhanger situation. Well, technically only one of them is, but the other friend is helping him. Look at this person hanging, literally hanging by the thread. Correct? The other person trying absolute best to make sure to pull the person upwards, I hope. But the idea is, which I want you to appreciate, is something else. The idea is that if the person who's falling down falls by some amount X, the poor guy on the top helping goes down with him because they are tied together with the rope. It's not about the person hanging. It's not about the person saving. It's not about the intention of the person saving. It's actually about the rope, because the rope is inextensible. And guys, that is constraint. That is the restriction, that the length of the rope remains constant. Rope cannot change its length. Look at that scenario which I just showed you into a, let's say, a problem context. You have two masses, M1 and M2. If the mass M2 falls down by an amount X, let's say, don't you think that M1 has to go right with the exact same amount X, because length of the rope cannot change owing to its inextensibility. What is the constraint here? Constraint is inextensibility. And what is the consequence of the constraint? The consequence is that both M1 and M2 have to move exact amount of distance in their respective direction to keep the length constant. Better? A little better? Let me make it even better. How about we address this concept with the help of another question, a better question, so that you understand not only the physics but also the math behind it. What you have is actually a smooth ring of mass M which can slide on a fixed horizontal rod. Let me read the problem out loud so that you have time to decode it. Then I will decode it for you before going into numbers. Deal? Let's read in parts. A smooth ring of mass M can slide on a fixed horizontal rod. Okay, the rod is fixed and the ring is slidable. Alright. A string tied to the ring passes over a fixed pulley and carries a block of mass M, C. Okay, as shown. So far so good. At the instant when the string and the pulley makes an angle theta, that is right now, find the relation between the velocity v of the ring and of the block. Which is the key word out here? The key word is, first of all, at an instant. What the examiner wants you to do is to find out the instantaneous relationship between the two velocities. Instantaneous means at this instant. Okay? Let me go through the physicality one more time. That what is the physicality? Physicality means the manner in which the system behaves. So basically, the block C, because of its own weight, will definitely try to fall down. So it falls down with an intention to take the ring along with it. But the ring doesn't go along, it goes along-ish, because the ring has a constraint that it can only slide on the horizontal rod. C goes down, ring can only go right. Are we sorted with the physicality of the system? C falls down, A goes right. Let's understand the mathematics now. Careful. Mathematics is better understood in the reverse order. What do I mean by that? Let me show you. The ring A slides to the right, let's say by a distance x. the part AB trapped between the old position of ring and B, however, doesn't get the entire contribution X but gets a part of it. I want you to appreciate here a couple of things. Point number one, this is not the natural state of the system. I know C falls right first and then comes the ring. Agreed. But as I claimed before, mathematics is better understood this way. Same page? Okay. Next point. The displacement X, listen carefully. The displacement X is actually a very small displacement. I have drawn it bigger for the sake of your clarity. Okay? So, please understand this X is a minuscule, a very small, in fact, infinitely small, or in a better word, infinitesimal, which is actually a collaboration of two words, infinitely and small. So, X is very small. Agreed? Now, the third point. Third point is, because of the displacement of the ring to the right, the part string AB, which is trapped between the ring and the pulley, does not get the complete contribution X of the ring, but gets a part of it. In fact, how do I find out what is the part of it? If I drop a perpendicular from A dash on this old string length AB, this angle is 90 because I dropped the perpendicular. You have a right angled triangle. Cos theta in a right angled triangle is the ratio base or adjacent. Let me call this point as P. AP upon the hypotenuse, which is A dash. Correct? Or AP is equal to A dash times cos theta. Who is playing A dash? A dash is nothing but the displacement, very small displacement of ring called X. X cos theta. And that's what AP is equal to. So my claim is actually legit. Due to the movement of the ring to the right by X amount, the string in between does not get the entire X but gets X cos theta. Now, keep your eyes glued to the screen. I'm erasing what I just wrote because it's going to appear again. So be with me. The thought is absolutely clear and let's continue what we started. All right, pay attention. What I just explained to you in the diagram, I will explain it to you again in the video. The agenda is very simple. The displacement of the ring is X, but the contribution received by the string is not equal to X, but it is actually X cos theta. Let me blow that part up for you for clarity's sake. Watch the diagram. X is A dash, the displacement of the ring. X cos theta is actually for the string. So the ring goes right by X amount. The string goes slack by X cos theta. But the string cannot remain slack. Somebody needs to compensate this X cos theta. And who steps up? The block C. So, ring goes to the right by X, string gets slack by X cos theta, and consequently, to compensate for it, C has to go down with X cos theta. The summary is, the ring slides to the right by X, string goes slack with X cos theta, and C goes down with X cos theta in the same amount. This is how the cookie crumbled. The constraint explained the inextensibility of the string. But the advantage is not done yet. I can take even more advantage of this situation. But before that, I will recall the disclaimers again. Step 1. Actually, I'm so habitual to steps. Disclaimer number 1. The displacement X was very small. Disclaimer number 2. The angle theta is instantaneous. What we are talking about is at this instant. If the instant changes, the value changes, but the pattern of the relationship is explained here. Okay? After all these disclaimers, what I'm trying to say is, from displacement, what is the rate of change of displacement? Velocity. What is the rate of change of velocity? acceleration. So the relationship I just found out in terms of displacement can be graduated further to velocity and further to acceleration. So A went right by x, string got slack by x cos theta, and C went down with the same amount x cos theta. Similarly, if A moves right with velocity v, C will also move down with the same ratio, that is the velocity v cos theta. If A goes right with acceleration a, in the same league, C goes down with acceleration a cos theta. And that, my friends, is the magic of constraint motion.